For decades, artificial intelligence researchers and neuroscientists have been working on parallel tracks, one building increasingly sophisticated algorithms, the other mapping the intricate workings of the human brain. Rarely have these paths converged in meaningful ways. That is, until now. The Topographic language model, TopoLM, developed by researchers at EPFL's Neuro AI lab in Switzerland, represents a watershed moment in AI development. Unlike conventional language models that learn through brute force statistical analysis, TopoLM demonstrates something extraordinary. It spontaneously organizes its internal structure to mirror how the human brain processes language. What makes this discovery so groundbreaking isn't just that an AI can emulate brain function. It's that this organization emerges naturally from a single, elegantly simple biological principle. By constraining artificial neurons to follow the same nearby neurons, similar functions rule that shapes our own neural architecture. TopoLM bridges the gap between artificial and biological intelligence in ways previously thought impossible. The neuroscience behind the breakthrough. To appreciate why TopoLM is revolutionary, we must first understand how the human brain processes language. Decades of neuroimaging research using fMRI and other techniques have revealed that language isn't handled by one general-purpose region, but rather emerges from a highly specialized, spatially organized network. When you read or hear language, your brain activates distinct cortical neighborhoods. Broca's area in the frontal lobe handles grammar and sentence structure. Wernicke's area in the temporal lobe processes meaning. Motor cortex regions activate when processing action words, run, throw. This organization isn't random. The brain appears to follow a fundamental principle of neural efficiency. Functions that work together should be located near each other. This minimizes the metabolic cost of long neural connections while optimizing processing speed. The remarkable insight behind TopoLM is that this same organizational principle, when applied to artificial neural networks, produces strikingly similar functional specialization. Just as the visual cortex spontaneously develops orientation-selective columns, how TopoLM works, engineering a digital cortex. At its core, TopoLM is built on a modified GPT-2 architecture, but with one crucial innovation. It imposes physical structure on what would normally be an abstract mathematical space. Here's how the researchers achieved this. The neural grid concept. Each of the model's 784 hidden units is assigned coordinates on a 28 by 28 grid, creating a neural map where every artificial neuron has physical neighbors. This spatial organization mimics how real neurons are arranged in brain tissue. The spatial smoothness constraint. During training, TopoLM optimizes two objectives simultaneously. Traditional language modeling, predicting the next word in a sequence. Spatial organization, ensuring neighboring neurons develop similar functions. Mathematically, this is expressed as SHA mathcal L, spatial, equal sign a frac 1, 2, left 1, text correlation, text activation similarity, text distance, -1, right, minus. Training process and parameters. The model was trained on 10 billion tokens from the FineWeb Edu corpus using 4 NVIDIA A100 GPUs over 5 days. Key hyperparameters included spatial loss weight, alpha equals sign 2.5, carefully tuned to balance language performance and neural organization. When researchers analyzed TopoLM's internal organization, they found something astonishing. The model had developed functional specialization almost identical to the human brain, verb and noun topography. Just like in fMRI studies, TopoLM's neural grid showed clear separation between verb-dominant regions, processing action words, remarkably close to the 0.96 correlation seen in human brains. The concreteness effect. Human brains show stronger neural specialization for concrete words, hammer, versus abstract ones, justice. Incredibly, TopoLM reproduced this exactly. Concrete words. This suggests the model isn't just memorizing patterns, but developing genuine semantic representations that mirror biological cognition. Language selectivity hierarchy. When presented with different types of linguistic input, TopoLM's activation patterns precisely matched human neural responses. Normal sentences, strongest activation, grammatical nonsense, Jabberwocky. Moderate activation, random word lists, weakest activation. This hierarchy mirrors exactly what neuroscientists observe when scanning brains during language tasks. Transformative implications across fields. TopoLM's breakthrough extends far beyond academic interest. It opens doors to revolutionary applications across multiple domains. 1. Interpretable AI. Unlike traditional black box models, TopoLM's spatial organization lets researchers literally visualize where different linguistic functions are processed. This could revolutionize AI safety and alignment research, debugging model biases and errors, developing more transparent AI systems. 2. Neuromorphic computing. By demonstrating that biological organization principles can work in AI, TopoLM provides a blueprint for energy-efficient AI chips with spatially organized circuits, fundamental neuroscience. Perhaps most excitingly, TopoLM can generate testable predictions about brain organization. EPFL researchers are already collaborating with neuroimaging labs to search for predicted but undiscovered language regions in the human cortex. Current limitations and future directions. While revolutionary, TopoLM isn't perfect. Key limitations include layer-specific organization. Unlike the brain's continuous cortical columns, each transformer layer has its own separate map. No recurrence. The model lacks the feedback loops crucial to biological cognition. Scale questions. Will these principles hold in 100 B+ parameter models? Future research directions could explore 3D topographic organizations spanning multiple layers, incorporating recurrent connections for working memory. Scaling. The approach to foundation model sizes, extending the principle beyond language to other cognitive domains. TopoLM represents more than just another incremental improvement in language models. It heralds a fundamental shift in how we approach AI development. By showing that simple biological principles can lead to emergent brain-like organization, it proves that high performance and biological realism aren't mutually exclusive goals. As we stand at this crossroads between artificial and biological intelligence, TopoLM lights the path forward toward AI systems that don't just process information, but organize knowledge in ways fundamentally aligned with how humans think. The implications for technology, neuroscience, and even our understanding of cognition itself are profound. The philosophical implications of brain-inspired AI TopoLM's success forces us to reconsider fundamental questions about intelligence. If artificial systems can self-organize in ways that mirror biological cognition, what does this say about the nature of thought itself? The model suggests that intelligence, whether biological or artificial, may emerge from universal principles of efficient information organization. This challenges long-standing debates about whether machines can truly understand language, as TopoLM demonstrates that brain-like representation isn't exclusive to organic systems. As we refine these models, we edge closer to answering whether consciousness could ever emerge from silicon, or if we're simply building increasingly sophisticated mirrors of our own minds. The future of AI-human collaboration. Beyond technical applications, TopoLM hints at a future where AI doesn't just assist humans, but collaborates in ways that align with our cognitive strengths. Imagine interfaces designed around how our brains naturally process information, or educational tools that adapt to individual neural learning patterns. By bridging the gap between artificial and biological intelligence, models like TopoLM could enable seamless integration of AI into fields like medicine, where doctors might consult diagnostic systems that think in neurologically familiar ways. This symbiosis could redefine human-machine interaction, making AI less an external tool and more an extension of our own cognitive capacities. Ethical considerations in biologically aligned AI. As we develop AI that increasingly resembles human cognition, new ethical dilemmas emerge. If a model organizes knowledge like a brain, does it experience analogs of human biases or vulnerabilities? TopoLM's interpretability offers opportunities to address these concerns proactively. We can audit where prejudices might crystallize in its neural regions. However, it also raises questions. Should AI have rights if its processing mirrors biological intelligence? And how do we prevent misuse of systems that potentially mimic human thought patterns too closely? These challenges underscore the need for ethical frameworks to evolve alongside the technology, ensuring brain-inspired AI serves humanity's best interests. TopoLM isn't just another AI breakthrough. It's a revolutionary step toward brain-inspired computing that could reshape how we develop intelligent systems, from more interpretable language models to neuromorphic chips and even medical applications. If you're as excited about this fusion of neuroscience and AI as I am, hit like, subscribe for more deep dives into cutting-edge tech, and let me know in the comments what aspect fascinates you most. For more insights on AI's evolving landscape and how it's transforming our world, visit judyofmarketing.com. Thanks for watching, and I'll see you in the next video, where we'll keep exploring the future of intelligent systems.